I'm going to discuss statistical thermodynamics for this CSIR coaching program. Students, I'm going to discuss from the fundamentals. So if you have any doubts, you please stop me wherever you want. Okay. Let me get into the topic. So the topic that we are going to discuss is statistical thermodynamics. Right. Yeah. As we all know that macroscopic properties, that is properties associated with the bulk substance, properties associated with the bulk materials, say for example thermodynamic properties in general, molar entropy, molar Gibbs free energy, right? These are all called macroscopic properties, right? So to study or to learn the macroscopic properties of bulk substances, we have classical thermodynamics. We have classical thermodynamics or simply classical mechanics. Okay. As far as chemistry, we can use the term classical thermodynamics. So using classical thermodynamics, we can study the macroscopic properties of substances. Here, the macroscopic properties that I mean are entropy, internal energy, enthalpy, like that. I repeat once again. See here, the macroscopic properties that I mean are actually thermodynamic properties. Okay, internal energy, enthalpy, entropy, like that. Then microscopic properties of substances, right? For example, here microscopic properties means atoms, molecules, right? Atom, molecule. The properties of these can be studied using quantum mechanics. Okay. So to study the bulk properties or macroscopic properties, we have classical thermodynamics. Okay, you might have learned about first law, second law, third law, right? In classical thermodynamics. Then you may also familiar with the quantum mechanical aspects, right? How to identify wave functions of a particular energy level, right? And what are all the quantized energy levels for a given system, right? Those things we can get from quantum mechanics. Okay, so these two are familiar with that for us, right? Classical thermodynamics as well as quantum mechanics. These two are very familiar. Using classical thermodynamics, we can learn macroscopic properties. Using quantum mechanics, we can study microscopic properties, right? Microscopic properties associated with atoms and molecules. Now, suppose if I take a gas in a container, okay, say for example, hydrogen gas. Listen, the macroscopic property, say for example, pressure of the gas. Pressure is a macroscopic property. We all know that the macroscopic property definitely depends upon the microscopic properties associated with the substance. Okay, so each molecule, each hydrogen molecule contributes to the total pressure. Okay, so somehow we can connect the microscopic properties, okay, to the macroscopic properties. Or we can say in the other way, we can predict or we can determine macroscopic properties using the microscopic properties present of the constituent particles present in the substance. Okay, so classical thermodynamics is used to calculate or determine macroscopic properties of the substance. Quantum mechanics is used to find the microscopic properties of the substance. Now, using the microscopic properties, okay, using microscopic properties, we can determine the macroscopic properties, right? How? Listen, we cannot simply add the microscopic properties of each and every individual particles, and so that we can calculate that. No, that is not the method. If you do that, If you do like that, definitely you'll get a wrong result. So this particular connection should be done in a very specific way, right? How to connect or how to determine macroscopic properties using the microscopic properties of the particles present in the system. How to do that? For this, we have a branch of science called statistical thermodynamics. So try to understand where this statistical thermodynamics is actually useful, right? It is actually used. The statistical thermodynamics play an important role in finding macroscopic properties using the microscopic properties of the particles or atoms or molecules as present in the bulk substance. Okay, yeah. So this is the introduction about statistical thermodynamics. Why do we need statistical thermodynamics? Okay, so to find the macroscopic, we have macroscopic properties. We have microscopic properties of the atoms or molecules of the constituent substance present in the bulk substance. Okay. Now, how to connect these two? Using microscopic properties, how to find the macroscopic property, right? For this, we are going to use a branch of science called statistical thermodynamics. Okay, so it is interconnecting classical thermodynamics and quantum mechanics. Then, to begin with the statistical thermodynamics, first of all, we should know what is meant by a macrostate and what is meant by a microstate. Yeah. So so keep this in your mind. Statistical thermodynamics is actually acting as a bridge between classical thermodynamics and quantum mechanics. Okay. Now, listen. Suppose if I take, say, for example, I have a system containing some gas. Say, for example, hydrogen molecules are there. Okay, 1 mole of hydrogen molecule or 2 mole of hydrogen molecule. Okay, whatever it is. Now, suppose if you want to find a specific property, right? Then specific macroscopic property. Then what we have to do? We have to choose the quantized energy levels correspond to that property. Okay, so suppose I'll take the rotational levels of hydrogen molecules. Right? You know very well, for hydrogen molecule, using quantum mechanics, we can find the quantized energy levels. I repeat once again, these levels may be rotational levels, or maybe vibrational levels, or maybe electronic level, or maybe translational levels, right? Whatever it is. Okay, so using the quantized energy levels, which we can find from quantum mechanics, okay, what we are going to do, we are going to calculate the macroscopic properties, okay, of the gas, right? The macroscopic property can be a pressure, or can be enthalpy, molar entropy, molar Gibbs free energy, whatever it is. We can find the macroscopic properties. We can determine the macroscopic properties, right, using the quantum mechanical information. So if a substance is given, first to see what are the particles present in the substance, then you have to take the respective energy levels, right? Depending upon your macroscopic property, you have to choose the respective energy levels. Okay, and these energy levels can be obtained from quantum mechanics. So for the given particle, apply quantum mechanics and find out the required quantized energy levels. Then we have to distribute the total number of particles, right? See, this system has some number of particles, say n particles. We have to distribute these n particles. Here particle, I mean hydrogen molecules. We have to distribute these hydrogen molecule in these quantized energy levels. Okay, because at a given temperature and at a fixed volume, right? Some molecules may present in some level, some molecule may present in some other level, like that. So you have some distribution. Okay, yeah. So before begin with macrostate and microstate, keep this information in your mind. Okay, depending upon the macroscopic property that you are going to predict, right? You have to choose the respective quantized energy levels, right, using quantum mechanics. Okay, so for the particle, apply quantum mechanics and find out the quantized energy levels, right? The quantized energy levels can be rotational levels or vibration levels or translation levels or electronic levels, whatever it is. Okay, yeah, it depends upon your the macroscopic property. Yeah, now first let me introduce what is meant by macrostate. Yeah, macrostate, some people using the term configuration. In some book, you can see the term called distribution. Remember, macrostate, configuration, distribution. Okay, these are all actually one and the same, right? In book to book, they are using different names, but they all gives the same meaning. Okay, macrostate, configuration, distribution. Now, what is meant by macrostate? Say, for example, I'll take some levels, quantized energy levels of a molecule, right? These quantized energy levels may be a rotation level or maybe vibration level or maybe electronic level. Okay, it depends upon what property you are going to calculate. Okay, what information you want. Based on that, you have to choose the respective quantized energy levels. Repeat, these quantized energy levels can be obtained from quantum mechanics. Okay, now what we are going to do, so for the given system, we have n number of particles. We have to distribute these particles. This is very important. See, our system is homogeneous. Okay, this gas consists of only hydrogen molecules. So for all hydrogen molecule, these quantized levels are same. Okay, but if you choose mixture of gases, then you'll get other problems. Okay, just to begin with, what I'm going to do, I'm going to take a homogeneous gas. Okay, so for this gas, we have all the molecules are same molecules. For these same molecules, the quantized energy levels are same. Okay, now, one second. Okay, so macrostate. What is meant by macrostate actually? Macrostate gives you, or macrostate is the specification of, macrostate is actually the specification of number of molecules or number of particles. Particle is the common term we use. Okay, particle means it can be atom or molecule, whatever it is. So macrostate is the specification of number of particles in each quantized energy levels, in each quantized energy levels of a system. Okay, it is nothing but occupation index, right? So what is meant by that? Suppose, assume that I have 2 particles here, 1 particle here. Let me take here 4 particle, here 2 particle, and here 1 particle. Okay, so assume that I have a system where I have totally 7 particles. 4 particles are present in the ground level, 2 particles present in the first level, first excited level, and 1 particle present in the 4th excited level. Okay, now I'm going to give you the specification of number of particles in each level, also called occupation index. Specification of number of particles in each quantized energy level of a system. This is also called as occupation index. So I'm going to denote, right, number of particles in each level. So in the ground level, we have 4 particles. In the first exit level, we have 2 particles. Third level is empty. 4th level is empty. And in the 5th level, we have 1 particle. Okay, this is what we call as occupation index, right? So at a given temperature, at a particular time, right? Each and every level has some number of particles, right? If you specify the number of particles in each level, that specification is what we call as macrostate, also called configuration, also called distribution. So what is macrostate? Macrostate is nothing but the specification of number of particles in each energy levels, each quantized energy levels correspond to the particle. Okay, yeah. So try to understand what is the meaning of this. Now, let me give one more example. So this is one macrostate, right? This is one macrostate, right? Now, using the 7 particles, I'll give another distribution like this. Here I have 2, 1, 1, here 1. So totally we have 6. I'll put one more here. Now I have another distribution like this. Okay, what is the occupation index? See, in the ground level we have 3 particles, next level 2 particles, next level 1, 4th level is empty, 5th level we have 1 particle. Okay, this is the occupation index for this distribution. Okay, so this is also called as another macrostate. Okay, see, this macrostate are not same. Why? Because the occupation index indices are different. Okay, if 2 different distributions, right? If 2 different distributions have different occupation indices, then we can say that these 2 distributions as 2 different macrostates. Okay, yeah. So try to understand what is meant by macrostate. Macrostate is nothing but it is the specification of number of particles. Students, listen carefully. Here, the particles I mean can be an atom or can be molecule. Okay, I'm using the general term particle, right? So it is a specification of number of particles in each energy levels of a system, right? This is what we call as macrostate, right? It is also called configuration and also sometimes called distribution. Now, what is meant by microstate? Okay, to understand microstate, let me consider a system like this. Okay, a system, right, consists of 2 particles. Here particles are distinguishable particles. I'll give you what is, I'll explain what is meant by distinguishable particle and indistinguishable particle and all as we proceed in this lecture. So time being, just keep this in your mind. We have a system containing distinguishable particles, right? And I have only 2 particles in the system. What is the total energy of the particle? Total energy is 3. Okay. Now for the particle, we have these quantized energy levels. These are all quantized energy levels of a particle. Now what I'm going to do, to get this total energy 3, we have to distribute the particle in such a manner that total energy should come to 3. How to do that? So I have only 2 particles now. So what I'm going to do, I'll place 1 particle in, okay, they are distinguishable particles. So to distinguish, what do I do? I'll use, yeah, I'll use letters. Okay, so assume that this is 1 particle and this is another particle. Okay, so particle A has energy 0 and particle B has energy 3. Since they are distinguishable, I'm using the notations A and B. Okay, now listen, what is the macrostate correspond to this? Okay, what is the occupation index? Okay, right, in ground level we have 1 particle, next level 0, next level 0, and the 4th level has 1 particle. Okay, so this is one macrostate. Now observe this carefully. If I swap these 2 particles, I'll place A here and B here because A and B are not same. Okay, they are distinguishable, right? So if I swap the 2 particles, right, now listen, what is the macrostate correspond to this distribution? You'll get the same result. So that means these 2 are 2 different ways of getting this macrostate. Students, observe carefully. This distribution and this distribution, okay, these 2 are 2 different ways of getting this macrostate. And these two are actually called microstate associated with this macrostate. Okay, so this macrostate is associated with the two microstates. Okay, so what are microstates? Very simple. Microstates is nothing but the unique way of getting each unique way of getting a particular macrostate is what we call as microstate. I'll write here. So what is microstate? Each unique way of getting a particular macrostate, right, is called a microstate. So this is one microstate, this is another microstate. So for this macrostate, we have two possible microstates. Okay, so what is microstate? Very simple. It is each unique way of getting or obtaining a particular macrostate. Okay, so I'll use a symbol W, right, which represent number of microstates associated with this macrostate. So the macrostate, let me take this macrostate as A. So the macrostate A has two microstates. Okay, W symbol actually refers to statistical weight, also called number of microstates associated with the given macrostate. Right, so this macrostate A, I call this macrostate as A. This macrostate A has two possible microstates. Okay, yeah. Now let me give another macrostate for this. Right, keeping the total energy 3E. Right, keeping the total energy as 3E. Now total number of particles is 2. I'm going to give another distribution. Okay, how? We can place a particle A at energy level having energy E, then another particle B at energy level having energy 2E. Okay, now see, for this particle energy is E, for this particle energy is 2E. If you add these two, you will get the total energy as 3E. So we can get the total energy 3E, right, by distributing the particle in this way. So for this, what is the index? The index is ground level, no particle. First level we have one particle, second level one particle, then the fourth level is empty. So ground level 1, second level 0, sorry, ground level 0, first level, second level 1, third level 1, fourth level 0. Now see this distribution and this distribution. Are the two same? See, they are not same. Okay, so the occupation indices are different. That means this is a different macrostate. Okay, so this macrostate is called as a different macrostate. I'm representing that macrostate as B. So this is a macrostate, let it be B. Okay, so remember, macrostate is nothing but, okay, specification of number of particles in each level, right? For the same total energy 3E, for the total number of particle 2, we have two possible macrostates, macrostate A and macrostate B. Right, for macrostate A, we have two microstates. Now we will check for macrostate B how many microstates possible. Okay, listen, if I swap these two particles, I'll place particle A here, B here. Right, definitely, see, this distribution also have the same occupation index. Right, occupation index indices are same. Right, but we know very well the particles are distinguishable. So particle B and particle A are not same. Therefore, this is actually a different distribution, right? So this macrostate can be obtained in two different ways. This is one, this is two. The number of ways of getting a particular macrostate is what we call, each unique way of getting a particular macrostate is called microstate. So for this macrostate B, how many microstates possible? Yes, here also we have two microstates. Students, observe carefully. If I am a little fast, please tell me. I'll just slow down. So we have a system, right, where the total number of particles is 2. total energy is 3, and the particles are distinguishable, I said. For this, we have two possible macrostate. Okay, A, macrostate A, and another macrostate is represented as B. Okay, for the two macrostate, number of microstates are same. Okay, for macrostate A, number of microstate is 2. For macrostate B also, number of microstate is 2 only. So that means these two macrostates are equally probable. Okay, participant, please listen carefully. Since both these macrostate A and B have same number of microstates, okay, have same number of microstates, they are equally probable. Okay, then. Now, I'll take another example. So now I have particles which are distinguishable, but now I have 3 particles in the system. Sorry, a small disturbance. Okay. So particles here are distinguishable particles, and total number of particles is 3, and let the total energy is again 3. Okay. So what is the difference between the previous example and this one? In the previous example, the system had only 2 particles. Now the system has 3 particles. Okay. Now we can distribute these 3 particles, right, in these energy levels, right, such that we should get the total energy as 3. How to do that? I said it is distinguishable, so I'll represent these particles as A, B, C. Okay, so what I'm going to do, I'll place the particle A here, B and C, let it be in the ground state. So for particle B, energy is 0. For particle C also, the energy is 0. Okay, whereas for particle A, the energy is 3. Therefore, if you add all, you will get the total energy as 3. So this distribution, right, I'll show you what is this distribution corresponds to. This distribution is to ground level. The ground level is 1, sorry, 2 particle, next level 0, next level 0, and the last level has 1 particle. So this is the distribution, right, or this is the macrostate for this system, having total number of particle 3 and total energy 3. Okay, now listen, in how many ways we can attain this particular macrostate, right? Let us represent this macrostate as A, right? In how many ways we can attain this macrostate, right? So we can place, see, instead of particle A here, put particle B there. Okay, so see, this distribution also having the same occupation indices, right? So it corresponds to same macrostate. And you in another distribution, you place C, particle C here, and A and B here. Okay, this is also having the same distribution, right, or occupation indices, right? So this macrostate A can be obtained in 3 different ways. Okay, this macrostate can be obtained in 3 different ways, and each way of getting this macrostate is called a microstate. Okay, so this is one microstate, this is another microstate, this is another microstate. So what is meant by microstate? Microstate is nothing but each unique way of getting a particular macrostate. Okay, yeah. So for this macrostate, we have, for this macrostate A, we have 3 microstates possible for the system. Now, listen, we can get this number of microstate using formulas also. Okay, I'm not going to show you how to derive these formulas. Derivations are available, but I'm not going to do that. I'm going to give you only the formula, right? See, I'll write the formula here. W is equal to n factorial divided by pi into ni factorial. This is a shortcut formula. This formula is applicable for distinguishable particles. Distinguishable particles. Capital N represent total number of particles. So totally we have 3 particles here. Therefore 3 factorial divided by pi. This pi represent geometric progression we have to multiply. Okay, Ni represent number of particle in the ith level. So let me start from the ground level. In the ground level, we have 2 particles, so 2 factorial into why multiplication? Because we have pi symbol. Pi symbol indicate multiplication or geometric progression, right? So 2 factorial. Then the next level is mt 0 factorial. Next level is mt 0 factorial, and the last level has 1 particle, so 1 factorial. Okay, so what we'll get? 3 factorial is 3 into 2 into 1. 2 factorial is 2 into 1. 0 factorial is 1. 0 factorial 1. 1 factorial also 1. You know very well. 0 factorial and 1 factorial, right? These two are equal to 1. 0 factorial as well as 1 factorial, both are equal to 1. Okay, so if you use the formula 2 to get cancelled, you'll get the answer as 3. So you can find the number of microstate, right, using this simple formula. Okay, and this formula is applicable only for distinguishable particles. Okay, yeah, so this is one particular information. Keep this in your mind. Now, we can get this total energy 3E in another way also. How to do that? Yeah, let me show you. I'll use a different color. Yeah. Listen, we should get total energy as 3E. So what's the way? You place, oh, it's not visible clearly. Once again, let's change the color. Yeah. We'll place one particle, say A here, B here, and particle C here. This is another way of distributing the 3 particle such that we should get the total energy as 3. Listen, for particle C, energy is 0, leave it. For particle B, energy is E. For particle A, energy is 2E. So if you add all, you will get the total energy as 3E. But what is the distribution here? Or occupation indices? Okay, ground level has 1 particle, next level 1, next level 1, the last level has 0. Now see this distribution and this distribution, are the two same? They are not same. That means these two are different macrostate. For this macrostate, okay, let me take this macrostate as B. For this macrostate, how many microstates will get? Okay, listen, we can actually distribute and we can find out. That is one way, right? But by distributing the particle in different manner and getting the same macrostate, this is possible if you have only if you have few particles in the system, say 2 particle, 3 particle. Okay, for these cases it is okay. Suppose if we have Avogadro number of particles in the system, then we cannot manually distribute and we cannot get all the microstates. Okay, it's become very difficult. So in those cases we can use the simple formula to get the number of microstate directly. Okay, so if we use this formula now, what we'll get? So total number of particles 3 factorial divided by ground level has 1 particle, 1 factorial, next level has 1 particle, next level has 1 particle, and last level no particle, 0 factorial. And as we all know that 0 factorial value is 1, 1 factorial value also 1. Therefore, the answer is 6. Okay, because 3 factorial can be written as 3 into 2 into 1. Okay, and in denominator all the values are 1. So you'll get the answer as 6. What does it indicate? It indicates that this macrostate 1110, this macrostate, okay, can be attained in 6 different ways. Okay, and each way of getting this macrostate is called a microstate. So how many microstates are possible? For this macrostate, 6 microstates are possible. Right? Now, is there any other way of getting the total energy as 3E? Yes, we have another way. What is that? Place all the particle A, B, C at energy level E. Right? Now, for particle A, energy is E. For particle B, energy is E. For particle C also, energy is E. So total energy is E plus E plus E 3E. So you can get the total energy 3E, right, by distributing the particle in this way also. But what is the occupation index? 0, 3, 0, 0. Now compare this occupation index with the earlier two, right? That is the distribution A and B, right? So if you compare this distribution, this occupation indices with A and with B, definitely this occupation indices is different. Okay, so let me call this distribution as C. It is also called another macrostate. So for three distinguishable particle with the total energy 3E, we have three macrostates. Okay, A, B, and C. Okay, now what is the number of microstates associated with the macrostate C? How many microstates associated with the macrostate C? Right?
One.
Yeah. Hello, yes. Yes, participant, any doubt? Yeah, I think you said some answer. You said 1, I think so. Yeah, it's correct. Yeah, the total number of particles is 3, C3 factorial divided by ground level 0 factorial, next level 3 factorial, next level 0 factorial, next level 0 factorial. So the answer is 1. Answer is 1. Now, listen, in the previous example, we had a system with 2 particles. And for the 2 particle, we got 2 possible macrostate. And for each macrostate, we got number of microstate as 2. Okay. So, and I said the 2 macrostates are equally probable. But now, see, in the second example, we have 3 macrostates A, B, C. But for macrostate A, we have only 3 microstates possible. For macrostate B, we have 6 microstates possible. For macrostate C, we have only 1 microstate possible. Now, which macrostate is more probable if you ask? Okay, we can say directly that the macrostate B is the most probable macrostate, okay, for this system. Okay, participant, are you clear in that? If you have any doubt, you please stop me and ask questions. Okay. Yeah, now I think now you understood what is meant by macrostate and what is meant by microstate. Yes, student, any doubt? Hello, participants.
Sir, this one more time, solunga, sir. One more time, can you please explain?
Yeah, yes, no problem. Listen, see in the previous example, see here, in this example, see the system has only 2 particles. Okay, for this 2 particle system, we have 2 possible macrostate A and B. And for both macrostate, number of microstate associated with the macrostate is only 2. See, here also 2, here also 2. Okay, so that means these 2 macrostates are equally probable, right? Whereas if you come to second example, in the second example, I have 3 particles in the system, right? For this, we have 3 possible macrostates, but these macrostates have different values of microstates. See, A is having 3 microstate, B is having 6 microstate, and C is having 1 microstate. So the microstates are not same now. In this case, I can say that the one having maximum value of microstate, okay, can be called as most probable macrostate. Are you clear now?
Yes, sir. Thank you, sir.
Yeah. So among these, which one is most probable? Among these 3 macrostate, which one is most probable?
B.
B. Very good, very good. B is the most probable macrostate. Okay, yeah. So keep this in your mind. In this way, any system, whatever system it is given, okay, you can find the most probable macrostate. But there is a problem. Okay, when we get problem, if we have huge number of particles, right, then it becomes very difficult to find the most probable macrostate. Okay, let me come to that later. Before that, I'll introduce another important term called thermodynamic probability. Okay, listen, the symbol that I used already, W, is what we call as thermodynamic probability. Okay. Yeah. This is a symbol we use for thermodynamic probability, W, also called statistical weight. Okay, mathematics people mathematics people call this a statistical weight, but in chemistry, very specifically in statistical thermodynamics, we never use the term W, statistical weight. Instead, we use the term called thermodynamic probability. Okay, thermodynamic probability is usually represented by symbol W. Sometimes you can see the symbol omega also. Okay, you can use both the symbol, but I'll tell you when we should use this, when we should use this. Okay, yeah. Now, before that, what is meant by thermodynamic probability? Right? What is meant by thermodynamic probability of a system? Very simple. Thermodynamic probability, okay, is nothing but number of microstates. Is nothing but number of microstates associated with a given macrostate. Very simple. See, we actually discussed two examples. Okay, and in example 1, I told you there are two macrostates possible, A and B. Okay, for macrostate A, we got 2 microstates. For macrostate B also, we got 2 microstates. Then in the second example, okay, we got 3 macrostates, A, B, C. For macrostate A, we get 3 microstates. For macrostate B, we got 6 microstates. And for macrostate C, we got 1 microstate. Okay, so what is thermodynamic probability? Thermodynamic probability of a macrostate. I repeat, thermodynamic probability of a macrostate is nothing but the number of microstate associated with the given macrostate. Okay, yeah. So thermodynamic probability is simply nothing but number of microstates associated with a given macrostate. That's all. Right? And remember, thermodynamic probability value, the least value is actually 1. Right? It can have value, right, usually above 1. Right? At 0 Kelvin, if all the energies are ceased, become 0, right, then W can be equal to 1. But at all other temperatures above 0 Kelvin, okay, W will be usually greater than 1. Okay, listen, you might have learned about probability in mathematics, called mathematical probability. See, mathematical probability is different. Mathematical probability is different. You know very well, mathematical probability for a particular event, okay, will be in between 0 and 1. You know very well, right? The lowest possible value is 0, the highest possible value is 1, and probability can be in between 0 and 1. This is called mathematical probability, but remember, don't confuse mathematical probability and thermodynamic probability, okay, in our statistical thermodynamics. Okay, don't confuse these two. They are entirely different. Okay, thermodynamic probability is nothing but number of microstates associated with a given macrostate. Okay, least possible value of thermodynamic probability for a given macrostate is 1, least value, and it can have any value greater than 1, right? Whereas mathematical probability, least value is 0 and the maximum value is 1, right? So in here, you should know the difference between these two. Okay, yeah, thermodynamic probability and mathematical probability, they are not one and the same, right? Keep this in your mind. Now, this is what we call as thermodynamic probability. Now before going to see some more aspects here, let me introduce what are the different types of particles that we are going to handle here. We classify particles into 2, distinguishable particles and indistinguishable particles. Hello? Hello, any doubt? Okay. Feel free to ask doubts, right? Whatever doubt comes to your mind, please feel free and ask, right? தமிழ்ல கேக்குறதாலும் கேளுங்க, ஒன்றும் பிரச்சனை கிடையாதுப்பா. Whatever doubt comes to your mind, please ask me. Right. So in statistical thermodynamics, very specifically in chemistry, we are going to handle systems containing particles. I told you the particles may be atoms or maybe molecules. Okay, we classify these particles into two: distinguishable and indistinguishable. Right? What are distinguishable particle? You can differentiate the particle at any instant of time. Say, for example, if I take a crystal, okay, assume that I have a crystal here, okay, and I have a particle here and another particle here. Okay, let us take this as x-axis, this is y-axis, and this is z-axis. Right? And this particle has some coordinate x1, y1, z1, and this particle has some coordinate x2, y2, z2. Listen, as long as the crystal remains as crystal, okay, some equilibrium vibrations will be there, but even then the position, equilibrium position remains same. Okay, so I can very well distinguish, right, this particle 1 and this particle 2, right, at any instant of time. I can easily distinguish these two particles because these particles are not undergoing any translational motions. Okay, so since there is no translational motion, these two particles remains in the same position. Listen, I didn't say that the particles are not moving. It is moving, called the equilibrium vibration should be there. Since it is equilibrium vibration, right, the equilibrium position remains the same. Therefore, we can distinguish the two particles at any instant of time. Okay, listen, earlier I have I have represented distinguishable particle with the symbol A, B, C and all. But remember, suppose if we take a crystal, right, a homogeneous crystal where all the atoms are same atoms. Okay, here I have atom A, here also I have the same atom A. The entire crystal is a homogeneous crystal. All the atoms are same atoms. Okay, and they are identical atoms, same, identical, same size, same mass, same energy, whatever it is, right? They may have same properties. I repeat once again, they may have same size, okay, same mass, same volume, right? Let it be like that. So what I'm trying to say is, listen, distinguishable means it doesn't mean that one is oxygen molecule, the other one is nitrogen molecule. No, it is not like that. Okay, here in this crystal, all the atoms are same atoms only. But I'm saying that these particles are distinguishable in the sense that, okay, I can distinguish the two particles, right, at any instant of time, okay, using the coordinates. I can distinguish, very well distinguish. Are you able to understand? That's why these particles are called as distinguishable. Okay, so நீங்க தப்பா understand பண்ணிக்காதீங்க. Distinguishable means one is nitrogen molecule, other one is methane molecule, not like that. Okay, here all molecules or all atoms are same atoms, right? But since they are not undergoing any translational motion, I can say that the particle 1 and particle 2, though they are same atoms, right, I can distinguish these two particles, right, using some technique. Okay, that's why we call these particles as distinguishable particles. Otherwise, right, all other properties are same actually for both the particles. Okay, but if you take a gas, hydrogen gas, say for example, in hydrogen gas, see, in the gaseous state, molecules undergoing translational motions with very fast very high kinetic energy. Since kinetic energies are very high, right, it is very difficult to track each individual particles. Okay, we cannot distinguish one particle from the other particle. Okay, so similarly, suppose if we take a metal, in metal, the free electrons of metal, the free electrons are actually moving like a gas. You might have learned this in your UG, right? And we cannot distinguish one free electron from the other free electron because it is randomly moving here and there. Okay, and all electrons are, they have same properties. Okay, we cannot distinguish them. So in those cases, we call the particles as indistinguishable particles. So try to understand what is the meaning for the distinguishable particle and indistinguishable particle. Okay, the word distinguishable is mainly applicable for crystalline states. Okay, yeah. Now, then to study the distinguishable particles, right? We have a statistics called Maxwell-Boltzmann statistics. Okay, we call this statistics also as classical statistics. It is a classical statistics. To study indistinguishable particles, right? We use statistics called quantum statistics. Quantum statistics. Okay, right. When you utilize the word quantum, immediately, okay, the point that comes to our mind is what is the spin of the particle, right? So for quantum state, for quantum particles, you have to see the spin. You know very well, particles may have half integer spin and integer spin. If particles have half integer spin, if spin values are half integer, 1 by 2, 3 by 2, 5 by 2, etc., those particles, right, can be handled with the statistics called Fermi-Dirac statistic. Okay, if particles have integer spin 0, 1, 2, 3, remember this is very important. Even 0, right, is an integer spin. Okay, so yes, the spin values are 0, 1, 2, 3, 4 for particles. We call those particles, those particles can be handled with a different statistics called Bose-Einstein statistics, right? So remember, depending upon the particle or depending upon the system that you are going to study, okay, you have to utilize these statistics carefully. Okay, so when we should use Maxwell-Boltzmann statistics, when we should use Fermi-Dirac, when we should use Bose-Einstein statistics, right? These informations, okay, should be known, right? For distinguishable particle, we are going to use Maxwell-Boltzmann statistics. For indistinguishable particles, right, we are going to use quantum statistics. In quantum statistics, we have two. One is Fermi-Dirac, the other one is Bose-Einstein statistics. Okay, yeah, keep this in your mind. Then, any doubt up to this? Participants, if you have any doubt, please ask me. Okay, listen, so till now, I have introduced few terms like macrostate, microstate, thermodynamic, probability, right? Then I have introduced what is meant by distinguishable and indistinguishable particles. Okay, then, and what type of statistics supposed to be used for a given type of system. Now, okay, before begin with, let me give you these shortcut formulas. Actually, we have derivation for these formulas, but this is not the right class for deriving everything. So I'm going to give you only the formula. Okay, listen, to find the number of microstate, also called thermodynamic probability. Okay, for distinguishable particles, we can use this formula. And when we should use this formula, listen, this formula is applicable for distinguishable particles. Distinguishable particles, whereas these two formulas should be used for indistinguishable particles. Okay, now for distinguishable particle, listen, I'll give here. Suppose if the quantized energy levels, right, for a given molecule, you may have quantized energy levels. If the quantized energy levels are non-degenerate, students observe carefully. If the quantized energy levels are non-degenerate, what is non-degenerate? See, the ground level has only one state. Next level has only one state, one state, one state. If all the energy levels have only one state, right? If each and every energy level has only one state, we call that system, or for this type of system, okay, we use this formula to calculate statistical weight or thermodynamic probability. Suppose if energy levels are degenerate, sometime depending upon your particle, the molecule, right, the energy levels may be degenerate also. If you have degenerate energy levels, then to find the thermodynamic probability, we use this formula. So remember, these two formulas are applicable for distinguishable particles. When we should use the first one and when we should use the second one. Okay, the first one and second one. The first one should be used if the energy levels are non-degenerate. The second formula should be used if the energy levels are degenerate. Okay, so keep this in your mind. Then for Fermi-Dirac, we should use this formula. For Bose-Einstein, we should use this formula to calculate thermodynamic probability. Here, what is capital N represent? Capital N represent total number of particles. Total number of particles, and small ni, that indicates number of particles in the ith level. Number of particles in the ith level. Ith level. Okay, and what is Gi? Gi is nothing but degeneracy of each level. Degeneracy of ith level. Okay, right. So suppose if we take ground level, right? How many states are there? Right, that is nothing but degeneracy of the ground level. Right, it may be 10 or 20 or whatever it is. Okay, so what is Gi? Gi is nothing but degeneracy of the ith level. Right, degeneracy means number of states available in the energy level I, or in the ith energy level. Okay, yeah. So keep these formulas in mind. Actually, we can derive these formulas, but we don't have that much time to derive, to do all these things. So I'll give you the formula in the beginning itself. Okay, just keep this in mind. Now I have told you we can find the most probable macrostate. See, I have given two examples, right? In example 1, I told you the two macrostates are equally probable. In example 2, I told you the macrostate B is more probable or most probable. Now, can we use this idea to find most probable macrostate? Okay, having say a system containing say Avogadro number of particles. Can we do like that? Okay, yeah, it is now it is difficult. Okay, it is difficult in the case of a system having a huge number of particles, right? And remember, it is well known that for each thermodynamic for each macrostate, students observe carefully. We have worked out two examples, right? So like that, if you take 4 particle, 5 particle like that, and if you find ln W versus Ni, okay, plot ln of W for each macrostate versus a particular level, ith level, number of particles in the particular level. If you see, listen, for most systems, okay, you will get a graph like this. You'll get a graph like this, right? With a small number of particles, right? People have identified this. Okay, and what is the most probable macrostate? Yes, this macrostate. This macrostate. This is the macrostate having the most probable value. Okay, now how to find out this most probable macrostate? It's very easy. You know, well, we have a maxima here. So the slope at this maxima should be equal to 0. So dou ln W by dou Ni, called the slope. Okay, the slope should be 0. If you put the slope equal to 0, you will get the maxima directly. So to find the most probable macrostate, okay, you need not distribute the particle and you need not do anything. Okay, just use this formula, dou ln W by dou Ni. But what is required for this? You must know what is the general formula, okay, for W for your system. Okay, I have given for most probable macrostate, I'm sorry, for Maxwell-Boltzmann, for Fermi-Dirac, for Bose-Einstein, I have given the general formula. If you know the general formula, take logarithm of that, then differentiate with respect to dou Ni, put the value equal to 0, you will get the most probable macrostate directly. Okay, yeah, students, I repeat once again, what is most probable macrostate? See, it is the macrostate having highest thermodynamic probability. I repeat, for a system, 2 or more macrostates may be possible. Among the possible macrostate, the one having maximum value of thermodynamic probability, or W, is called the most probable macrostate. Okay, so most probable macrostate is the macrostate having highest thermodynamic probability value. Highest thermodynamic probability value. Simple. And why do we need to do that? Why do we need to find out the most probable macrostate? Remember, equilibrium properties. Students, observe carefully. Equilibrium properties, right? Okay, equilibrium properties are mainly, okay, more 99.9%. Okay, equilibrium properties of a system, right, is almost 99.9% is due to the most probable macrostate, or the most probable macrostate decides almost 99.9% the equilibrium properties of the system. So suppose if you want to calculate equilibrium properties associated with the system, right? So that is what is the internal energy, average internal energy, what is the average entropy, what is the average Gibbs free energy. Okay, so to find the equilibrium properties, right, we should know the most probable macrostate. Why? Because when you take a system having more number of particles, Avogadro number of particles, right, the most probable macrostates decides the equilibrium properties. Okay, so because our goal is to find, what is our goal? What is the use of statistical thermodynamics? Statistical thermodynamics is a branch of science by which you can determine macroscopic properties, equilibrium properties, or non-equilibrium properties. Yeah, macroscopic property can be equilibrium property or can be non-equilibrium property, right? What we are going to learn under statistical thermodynamics is only equilibrium properties. To determine non-equilibrium properties, or we have another thermodynamics called irreversible thermodynamics. You might have learned about that. Irreversible thermodynamics. I'm not going to teach you irreversible thermodynamics here. Okay, so to understand equilibrium properties, right, we require most probable macrostate. To find the most probable macrostate, okay, we can use this technique. Okay, if you want to use this technique, you must know the general formula for W. And I have given the general formula for Maxwell-Boltzmann, Fermi-Dirac, Bose-Einstein already. Okay, but listen, the type of system that we are going to handle is not that simple. Listen, suppose if you have y and x, right, and if you have a curve like this, then dy by dx, if you put it equal 0, you'll get the maxima directly. Okay, but in this case, we have two constraints. We have some constraints here, right? What's the constraint? You have to maximize, you have to find the most probable macrostate, keeping this in mind that n should be constant and e should be constant. I repeat, see, we are going to maximize the function w to find the most probable macrostate. If you want to maximize a function, okay, dy by dx formula is okay, but the problem is we have two constraints. What is the constraint? Total number of particles should be constant and total energy should be constant. Okay, keeping these two constant, you have to maximize. Okay, for this you require a special technique, right, called what is that? Undetermined multipliers. Lagrange undetermined multiplier techniques are there. So we have to use that technique to find the most probable macrostate. Okay, yeah, students, up to this, any doubt? Most probable macrostate என்றது என்னன்னா, எந்த macrostateக்கு thermodynamic probability maximum value வருதோ அதுதான் most probable macrostate. Okay, how to find out the most probable macrostate? நம்ம முன்னாடி பண்ண மாதிரி example 1 example 2ல நம்மளே டிஸ்ட்ரிபியூட் பண்ணி பண்ணோம் இல்லையா, அது மாதிரி பண்ண முடியுமானா it is difficult. Yeah, for a few number of particles is okay. For 3 particle, 4 particle, 5 particle is okay. But if you handle a system with Avogadro number of particles, okay, then it is very, very difficult to find the most probable macrostate. Okay, so we have to use some alternative technique. All right, and the 2 particle, 3 particle, 4 particle, 5 particle examples that gave some idea. What's the idea? If you plot ln W versus Ni, okay, you will get a curve like this. So the most probable macrostate can be obtained by just differentiating this dou ln W by dou Ni. That will give you the answer as 0. If you put the answer as 0, you will get the maxima directly. But here there is other problems. What are the other problems? We have to maximize W in such a manner that keeping we should maximize keeping N constant and E constant. Okay, for this we have to use some special technique. See, this formula dy by dx equals 0. In this case, there is no constraints at all. Without constraint, it is okay. But now we have 2 constraints. One is total number of particles is constant. The other one is total energy is constant. Okay, for this we have to use some special technique called there is undetermined multiplier technique. Okay, Lagrange's undetermined multiplier technique. Yeah, that will discuss if possible in this lectures. Now, Stirling's formula. Yeah, listen. When you use this formula, dou ln W by dou Ni equals 0. Okay, you will end up with because in W, see, in the general formula of W, we have factorials. Okay, we have n factorial, we have ni factorial and all, right? But keep this in your mind. The system that we are going to handle, okay, is a huge system containing minimum Avogadro number of particles. So these n values are very, 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 very high. You know very well in calculator, okay, you cannot find the value of 200 factorial itself. 200 factorial நம்ம calculator கண்டுபிடிக்க முடியாது. Syntax error காமிச்சிரும். Okay, suppose if you have Avogadro number, what is Avogadro number? 6.023 10 power 20, 10 power 23 factorial. How to determine that? Okay, yes, we cannot determine this using calculators. Then what we have to do? Okay, this problem was first addressed by a scientist, Stirling. He gave a formula called Stirling's formula, according to which ln of n factorial is roughly equal to n ln n minus n. Okay, listen, this value, or if you use this, using this formula, if you calculate ln n factorial, from ln n factorial, we can find out n factorial. Okay, by taking antilog and all, we can find out n factorial. Listen, this answer will be very, very accurate if n is very, very large. Okay, that is the specialty about Stirling's formula. Okay, if you want to use Stirling's formula, okay, the number should be very, very large. If you use small number, say 5 factorial or 10 factorial, in Stirling's formula, you will get a huge difference between your result and the accurate value and the correct value. Okay, so Stirling's formula is very, very useful, right, if the number is very, very large. Okay, keep this in your mind. Now, yeah, let me introduce the first statistics called Maxwell-Boltzmann statistics, right? So in Maxwell-Boltzmann statistics, what type of particle we are going to see? We are going to see particles. Okay, the particles should be identical, right? By appearance, they should look alike. The particle should be independent. Independent means there should not be any attraction or repulsion between particles. Okay, okay, they are independent. Then last one, they should be distinguishable. What are distinguishable particles? That you know. Okay, yeah, I have given sad face here. I'll tell you why I have given sad face, right? As we go along in this lecture. Okay, yeah. See, what Boltzmann did was, even for gas, okay, Boltzmann utilized the formula and he predicted some value. Right? Later, people found that in the case of gas, we cannot take the particles as distinguishable particles. Okay, right. So that's why actually Boltzmann committed a mistake here, right? He, even for gases, he utilized the formula given for the distinguishable formula. He assumed the particles as distinguishable particle, but if you take a gaseous system, okay, the particles cannot be distinguished, right? The particles are indistinguishable. Yeah. Now listen. So for Maxwell-Boltzmann statistics, particles should be identical, independent, distinguishable. And there is no restriction on the number of particles in each energy level. Okay, listen. In each level, you can place any number of particles, even 5,000 particles you can place, 10,000 particles you can place. There is no restriction on the number of particles in each level. Okay. Then total number of particles should be constant, total volume should be constant, and total energy of the system should be constant. Okay. Yeah. Listen, we say that these are all called ensembles. Okay, what is meant by ensemble and all I'll explain in the next lecture. Okay, now I think I gave this formula already. If we have listen, if the particles are distinguishable, then we have two formulas to calculate thermodynamic probability. When we should use this formula and when we should use this formula, I have told you. If the energy levels are non-degenerate, use this formula. If the energy levels are degenerate, then use this formula to calculate thermodynamic probability. Okay, so we have formulas. We have general formula for W, right? Now we have to, so now the system consists of N particles, total number of particles is N, total volume is V, total energy is E. Now what we have to do, we should identify the most probable macrostate. Okay, so to find most probable macrostate, we cannot just like that, we cannot distribute the particle and we cannot calculate the number of microstates for each macrostate. That is very difficult to do. So what's the alternative idea? The alternative idea is calculate or use the formula dou ln W by dou Na. Calculate this and put the value equal to 0. And we have two constraints. What are the two constraints? Total energy should be constant. And if total energy is constant, what is total energy actually? Total energy is nothing but sum of number of particles in ith level into energy of the ith level. Okay. Observe this carefully. Observe this carefully. It's very important. What is EA? EA is nothing but quantized energy. Quantized energy values for each level of the given particle. This is obtained from quantum mechanics. Okay, as long as volume is constant, right? You know very well, if volume changes, these energies may change depending upon what type of motion that you take. Suppose if you take translational motion, you know very well, in the case of translation motion, if volume changes, translation energy levels get shifted. Okay, but for other cases, this EI remains constant. Okay, so in each level, what is the energy of the ith level? Then how many particles are present in the ith level? If you multiply these two, you will get energy for that level. Similarly, you do it for other levels also, then add all the values, you will get the total energy. Now, listen, you differentiate this with respect to Ni, dou E by dou Ni. Okay, here see EA is constant, right? So Ni is equal to 1. So what we'll get is EI. EA is constant here. Okay, or summation of EI. Yeah, summation of EI. Similarly, total number of particles is constant. What is total number of particles? So nothing but summation of number of particles in each level. Okay, in each level, how many particles are there? Just add all the values, you will get total number of particles. And if you differentiate this dou N by dou Ni, right? That should be equal to, yeah, I made a mistake. One second. I made a mistake. What is that? Yeah. Here this is correct. EI. Yeah. So here EA is constant. So if you differentiate Ni, you'll get the answer as 1. So summation of EI, that's correct. Here, if you differentiate, Ni, if you differentiate, it becomes 0. So dou N by dou Ni equal to 0. Okay, it's very simple, right? We'll discuss that later. Now listen, we have to utilize these conditions. These two are actually called constraints. Total energy is constant, total number of particles is constant. Using this constant, keeping these two constant, you have to maximize this function. Okay, then you have to use the Lagrange undetermined multiplier technique. Okay, finally, we will end up with this formula. I'm not going to do derivation here. I'm going to give you the final formula. The final formula is Ni by N equal to Gi into e power minus Ei by kBt over summation Gi into e power minus Ei by kBt. We will get a formula like this. Okay. Yeah, this is for degenerate case. For non-degenerate case, just remove this Gi, that's all. For non-degenerate system, you have to remove Gi. Now listen, what does this formula indicate? This formula will give you number of particles in the ith level of the most probable macrostate. This is what actually we want. Okay, in the most probable macrostate, okay, how many particle present in the ground level? How many particle present in the first level, second level, like that? Okay, so we can calculate the number of particles present in the ith level, right, for the most probable macrostate using this formula, right, where EA is the energy of the ith level, KB is Boltzmann constant, T is temperature. Okay, those things you know. Okay, yeah, and this is called the partition function. This denominator quantity is what we call as partition function. I'll discuss that later. Now this Ni by N is what we call as probability. So probability of occupying the ith state. Okay, what's the probability of occupying ith state in the most probable macrostate, right? Which is nothing but Gi into e power minus Ei by kBt over this summation of Gi into e power minus Ei by kBt. Ni by N is called probability of occupying ith state. Okay, yeah. So this formula will give you the probability, right? Probability of occupying ith state in the most probable macrostate. See, this formula is very, very important, right? This formula will give you number of particles in ith level in the most probable macrostate directly. Okay, that's the advantage of this formula. Now, see here, if you plot probability of occupying ith state versus temperature. See, this is actually constant. This denominator quantity, because as you change the temperature, some particle may go to higher level, some particle may count down, right? Whatever it is, the summation remains the same. Okay, partition function remains the same, right? Now listen, yeah, we'll discuss that later in a detailed manner. We'll do that in a detailed manner. As you increase temperature, see, temperature is here, it is in the denominator value. If temperature increases, this value will decrease. Okay, then once again, not with respect to temperature. Okay, yeah, we need to know about partition function for this. Okay, let me discuss that later. Okay, we'll do it in the later stage. Let it be as such. So I have given the formula for Maxwell-Boltzmann distribution. This is the formula for Maxwell-Boltzmann statistics. Okay, keep this in your mind. And this is the formula we use to calculate probability of occupying ith state in the most probable macrostate. Okay, now, yeah, this is very important. Listen, I have told you that the system that we are going to handle consists of a huge number of particles. Okay, so assume that I have a system. Okay, let us call this as a water bath. Okay, I have a water bath which consists of many boxes, and each box, okay, number of particle is same. I have same number of particle in each box. Okay, and volume of each box is also same, right? Then let us assume the temperature also same. Let us assume like that. I'm keeping temperature also same. Or yeah, listen. So, and these walls, the walls of these containers, small containers, they are actually diathermic in nature. Diathermic means they allow the exchange of heat. Therefore, the total energy of this system and total energy of this system and total energy of this system, they need not be same. Okay, we call this entire system as an ensemble. It is called an ensemble. So an ensemble consists of many systems. Okay, like this we have many systems, and each system consists of same number of particles. Okay, and same total volume, same temperature also. If you keep NVT constant, right, it is also called a canonical ensemble. Canonical ensemble. Okay, in each system, total number of particle, total volume, temperature, all the three are constant. If you keep these three constant, then this ensemble is called as canonical ensemble, right? And here in this canonical ensemble, the energy of this system, energy of this system, this energy of this system, they need not be same. Suppose assume that I have 5,000 systems here, 5,000 systems. Okay, in these 5,000 systems, some 100 system may have energy E1. Another 250 system may have energy E2. Another 300 system may have energy E3, like that. Okay, now what is the probability of occupying, right? Or what is the probability of having a system having energy EI? Okay, which is given by the formula. Yes, we have to use the same formula, GI into e power minus EI by KBT. I'm using capital E here. Capital E is nothing but total energy of the system. Okay, total energy of the system having energy EI divided by summation quantity GI into e power minus capital EI by KBT. Okay, listen, very important. Listen, this is actually the formula for ensemble, right? What we discussed earlier is the formula for single particles. Okay, so this denominator quantity is what we call as canonical partition function. Repeat. This denominator quantity is called canonical partition function, which we represented by the symbol Q. And in this partition function, you know very well, total number of particles is constant, volume is constant, and temperature is constant. If you keep these three constant, then this denominator quantity is called canonical partition function. Right? Yeah. But here, see, I have given a formula here where the partition function in which total number of particle constant for each system, total number of particle constant, total volume constant, and the energy constant. If you take energy constant, okay, it is this is not a canonical system. It is called a microcanonical system. This is actually a microcanonical system. If you keep number of particle, volume, temperature constant, we call that system as a canonical ensemble system. Okay, so this is actually ensemble partition function, right? Then see what are the values are fixed for each system. Okay, if N, V, E are fixed, it is called microcanonical system, a microcanonical partition function, right? Or okay, if N, V, T are constant, then it is called canonical partition function, right? And this is the formula for canonical partition function. Okay, where EA is the energy of the system, having energy EI. Okay, now this canonical partition function is related with the molecular partition function which we derived earlier. Okay, how? Listen, canonical partition function is equal to molecular partition function. Listen, for molecular partition function, total number of particle and total volume is constant. Okay, not the energy. See, here energy is constant, right? Total energy is constant, but the energies of each level, they need not be constant. Okay, so how Q, capital Q and small q are related, right? For this formula is applicable for distinguishable particles. Okay, we can write simply like this: capital Q. Don't worry about this NVE and all. We are going to learn that in a detailed manner as we go along in these lectures. So capital Q is equal to small q power n, right? Capital Q is the canonical partition function. Small q is the molecular partition function. Okay, or single particle partition function. This power n indicate number of particle, total number of particle present in the system. This formula should be used for distinguishable particles. Okay, yeah. Then second one, suppose if the particles are indistinguishable. Then we should use this formula, right? To this formula which is interconnecting the ensemble partition function and the molecular partition function. Capital Q, small q. Right? Yeah. So why I'm introducing this? Because ensemble concept is very important, which actually connect the classical thermodynamics and the quantum mechanics. Right? We'll discuss that later in a detailed manner. Now, listen, molecular partition function, small q. I'm going to use small q symbol for molecular partition function, which is given by the formula summation of Gi into e power minus Ei by kBt. Here, these Eis are the energies of the quantized levels. Whereas this Ei, see in the top, this Ei is the energy of the system. See the difference. Okay, yeah. So we are going to discuss molecular partition function and the related concept now. What actually molecular partition function tells you? Okay, suppose if molecular partition function is 100, what does it indicate? Listen, molecular partition function indicates that how many energy states or energy levels are accessible by the particle at a given temperature. Okay, so I'll write it in the next page. So what does this Q indicate? Right? What does this Q indicate actually? Q will give you, right? Molecular partition function will give you number of accessible states or number of states accessible by the particle at a given temperature. I repeat. Listen, what does this Q indicate? Q tells you number of states accessible by the particle at a given temperature. Listen, this Q is applicable for single particle partition function. Remember, for one atom, for one molecule, yes, we can use Q, molecular single particle partition function. What is the value of single particle partition function indicates? It indicates how many states are accessible by the particle, okay, at a given temperature, right? Say for example, if we have 100 states like this, okay, if I say Q is equal to say 3, what does it indicate? This particle has a system having one particle now. This particle can access up to 3 states. That's the meaning for this. Because at the given temperature, the particle can access only these 3 states. If you increase the temperature, it can access even more states. Even if you increase temperature further, it can even access few more number of states. Okay, so partition function will give you, right, how many states are accessible by the particle at a given temperature, right? Listen, for monoatomic molecules, see helium, neon, argon, okay, where helium, neon, argon all exist as atoms, right? So for single atoms, right, total molecular, that is single particle partition function, in the case of monoatomic molecule, can be calculated. Total single particle partition function can be calculated using these two partition functions. This is translational partition function and this is electronic partition function. This formula is applicable for monoatomic molecules. If you go to other molecules, diatomic, polyatomic molecules, okay, in that case, the total molecular partition function is equal to the product of these four partition functions, right? Translational, rotational, vibrational, electronic. Okay, so you have to see this system carefully. Suppose if a helium gas is given, right? In that case, we have to calculate only translational partition function and electronic partition function to find the total. Suppose if we take an hydrogen gas, right? Then we have to calculate translational, rotational, vibrational, electronic, everything, right? So the total molecular partition function, right, depends upon what type of particle that you are handling, right? Once you know this q, small q, we can calculate the ensemble partition function using the formula that I gave already, q power n for distinguishable particles, q power n by n factorial for indistinguishable particles. So once you know this, you can calculate the ensemble partition function. It can be canonical ensemble, it can be micro canonical ensemble, or it can be even grand canonical ensemble, right? So whatever may be a system we can use. Okay, we can calculate the ensemble partition function. Once you know the ensemble partition function, see, why do we need to calculate this partition function q? Listen, this partition function, right, is nothing but heart of, okay, see, for a human being, heart is very important, like that for to find the equilibrium properties of any system, okay, we must know q. We must know the ensemble partition function. Ensemble partition function, okay, plays a vital role, right, in determining equilibrium properties of the system. Okay, so the main goal, see, in quantum mechanics we say that once you know the wave function, then you can determine all the properties of the all the informations about the microscopic system. Okay, in quantum mechanics. Similarly, in statistical thermodynamics, okay, q plays a same role as psi, wave function psi. So if you know q, yes, you can get all informations about the, or you can determine all the equilibrium properties of the system. Okay, yeah. So keep this in your mind. We can derive the expression for translational, rotational, vibrational, electronic, everything, but I'm not going to derive everything here, but I'll give you the formulas, right? See, what is the formula for translational partition function? I'm not going to derive because we don't have that much time. I'll give you the final expressions. Okay? Translational partition function for 3 dimension, you know very well. To calculate translation partition function, we use either 1-dimensional box formula, 2-dimensional box formula, 3-dimensional box formula. But if you take a gas in a cylinder or in a container, okay, definitely the container should be 3rd dimension. So we have to use 3-dimensional formula. So, right, the formula is this 2 pi m kBT whole power 3/2 by h cube into V. Right? This is the formula we use to calculate translational partition function. See, this is a single formula applicable for all type of particle, whether the particle is monatomic or diatomic, triatomic, whatever may be the particle. For translational, as far as translational partition function is concerned, we have only one formula for all type of particles, right? Yeah, we can have alternative formula. Just modifying this, we can give formulas like this: V by lambda cube, where lambda is called thermal thermal de Broglie wavelength. Okay, thermal de Broglie wavelength. Now listen, what does this formula indicate? See, translational partition function is directly proportional to mass. Translational partition function is directly proportional to temperature. Translational partition function is directly proportional to volume. Okay, listen, if we increase volume, translational partition function increases. What does it indicate? Listen, if we increase the volume of the vessel, translational partition function increases according to the formula. What does it indicate? It indicates that, listen, the translational energy levels will shift if we increase the volume of the gas. Okay, it actually comes closer. See, suppose if we have translational levels like this for a system, right, at some volume V, if we increase the volume, so twice the volume V, what will happen? The translation energy levels comes closer. If energy levels comes closer, then particle can access more states, right? Particles can access more states. So Q value will increase, right? So keep all these things in mind, very, very important. Okay, if mass of the particle increases, translation partition function increases. If temperature increases, translation partition function increases. If volume increases, translation partition function increases. This is, we know, very simple. If temperature increases, we should supply heat. If you supply heat, molecule gains energy and goes to, and it can access higher levels also. So partition function will increase. But volume is very, very important. When you increase volume, why partition function increases, right? And very specifically, translational partition function. The reason is the translational energy levels depends upon volume. Okay, as you increase the volume, right, the translation energy levels comes closer. Therefore, particle can access even higher states. So partition function will increase. Students, observe this carefully. Partition function will give you number of states accessible by the particle at a given temperature. Okay, if Q is 100, the particle can access only 100 states. If Q is 200, the particle can access 200 states. Okay, so keep this in your mind. This is very, very important. So this is regarding translational partition function. Sir, shall I stop now? Hello?
Okay, sir. Okay, sir. Done.
Okay. Okay, sir. Students, if you have any doubt, please ask me. Let me answer that. Yes?
Students, question கேளுங்கப்பா. If you have doubt, please ask me. Unmute yourself.
Yes. Yes, ma'am. Definitely there's a link. Okay. Actually, in term symbol, you are calculating that L, capital S, and finally you are finding J, no? Capital J. And you say that 2J plus 1 will give you the degeneracy. 2J plus 1. That is nothing but electronic degeneracy. Right? Electronic degeneracy associated with this. Right? So now I have introduced only the translational partition function. Okay. We are going to see vibration, then rotation. Finally, we are going to see electronic. At the time of electronic partition function, we are going to use that formula. Okay. Well, yeah, we have link there. Yes. Any other? Thank you, ma'am. Thank you. Students, any other questions? உங்களால ஃபாலோ பண்ண முடியுதா? ஃபாலோ பண்ண
வால்யூம்.
ஹலோ, எஸ்.
இந்த வால்யூம் இன்க்ரீஸ் ஆனா பார்ட்டிஷன் ஃபங்க்ஷன் இன்க்ரீஸ் ஆகுது சார். அதை மட்டும் கொஞ்சம் கேட்டுடுங்க.
அதாவது ஆக்சுவலா வரல. இப்போ அக்கார்டிங் டு திஸ் ஃபார்முலா, this translational partition function and volume are directly proportional, right? நம்ம டெரிவேஷன் பண்ணா ஃபைனல் எக்ஸ்பிரஷன் இப்படி தான் வரும். So it shows that volume and translation partition function are directly proportional. Directly proportional என்ன அர்த்தம்? வால்யூம் இன்க்ரீஸ் பண்ணா translation partition function இன்க்ரீஸ் ஆகும். translation partition function இன்க்ரீஸ் ஆகுதுன்னா என்ன மீனிங்? ஓகே, ஒரு பார்ட்டிகிள் 100 லெவல்ஸ் தான் ஆக்சஸ் பண்ணி வச்சுக்கோங்களேன். நான் வால்யூம் இன்க்ரீஸ் பண்ணா 200 லெவல் ஆக்சஸ் பண்ணுது. இப்போ அது எப்படி பாசிபிள்? நம்ம எனர்ஜி கொடுத்தா பரவாயில்ல, எனர்ஜி கொடுத்தா பார்ட்டிகல் எனர்ஜி எடுத்துக்கிட்டு ஹையர் லெவல் போகுதுன்னு சொல்லலாம். நான் எனர்ஜி எதுவும் சப்ளை பண்ணல, ஐம் இன்க்ரீசிங் த வால்யூம். வால்யூம் இன்க்ரீஸ் பண்ணா எப்படி டிரான்ஸ்லேஷன் பார்ட்டிஷன் ஃபங்க்ஷன் இன்க்ரீஸ் ஆகுது அப்படின்னா, these translational levels, the energy levels, these levels depends on volume. Okay, அதனால தான் எப்பயுமே நம்ம என்ன பண்ணோம்னா சிஸ்டம் இது சாரி டிஸ்ட்ரிபியூஷன் படிக்கும்போது ரைட் we consider volume as constant. வால்யூம் கான்ஸ்டன்டா வச்சுக்கோங்க யூஸ்வலாவே. எதனால தான் இந்த ப்ராப்ளம் தான், ஏன்னா வால்யூம் இன்க்ரீஸ் பண்ணா very specifically for translational levels, right, the energy gap will decrease if you increase the volume. Okay, so நான் இங்க பாருங்க ஒரு எக்ஸாம்பிள் சொல்றேங்க, நீங்க டிரா பண்ணேன், பட் எனிவே I'll read once again. Suppose எனக்கு 4 levels இருக்கு வச்சுக்கோங்க. Now the particle can access only 2 levels at a given temperature வச்சுக்கலாம். So temperature constant. So how many levels the particle can access? Only 2 states. So partition function is 2 only. நான் இப்ப என்ன பண்றேன், I'm going to increase the volume. If I increase the volume, what will happen? The translational levels comes closer. If it comes closer, see this gap, this energy gap and this energy gap are almost same. So if the temperature is same, right, the particle can access all these 4 states. So partition function become 4. Are you able to follow? Temperature same தான், ஆனா வால்யூம் இன்க்ரீஸ் பண்ணா the gap between adjacent translation level will decrease. அது டிக்ரீஸ் ஆகிறதுனால எஸ் ஏன் டிக்ரீஸ் ஆகுது? ஓகே, நீங்க அந்த பார்ட்டிகல் 1D பாக்ஸ் பார்த்திருப்பீங்களே, பார்ட்டிகல் 1D பாக்ஸ்ல ரைட் வேர் த எனர்ஜி இஸ் ஆக்சுவலி டிரான்ஸ்லேஷன் எனர்ஜி, ரைட்? நம்ம கைனடிக் எனர்ஜி 0ன்னு வச்சுக்குவோம், ஐம் சாரி பொட்டன்ஷியல் எனர்ஜி 0ன்னு வச்சுக்குவாங்க. ஞாபகம் இருக்கப்பா? பார்ட்டிகல் 1D பாக்ஸ்ல inside the box potential energy is assumed to be 0 ன்னு சொல்லுவோம். potential energy assume 0 assume பண்ணிட்டீங்கன்னா அப்போ என்ன எனர்ஜி இருக்கும்? kinetic energy is nothing but translational energy, right? So translational energy is equal to n square h square by 8ml square வருதா ஃபார்முலா? இங்க L ன்றது என்ன? L ன்றது பாக்ஸ் லென்த் சொல்லுவீங்களே. இப்போ பார்ட்டிகல் 3D பாக்ஸ் போனாலும் அந்த L இருக்கும்ல, இங்க அந்த L இருக்கும் இல்லையா? அப்போ நான் என்ன சொல்றேன், இப்போ பாக்ஸ் இன்க்ரீஸ் பண்ண, அதாவது வால்யூம் இன்க்ரீஸ் பண்றேன், வால்யூம் இன்க்ரீஸ் பண்ணா L என்ன ஆகும்? பாக்ஸ் உடைய வால்யூமை இன்க்ரீஸ் பண்றதுனா L will increase, correct? L இன்க்ரீஸ் ஆனா இது என்ன பாக்குமா, இந்த எனர்ஜி ஆகும்?
எனர்ஜி டிக்ரீஸ்.
அதுதான் பாயிண்ட். வால்யூம் இன்க்ரீஸ் பண்ணா okay, energy decrease ஆகும். For each level energy will decrease. So the gap decreases. Gap decrease ஆச்சுன்னா பட் டெம்பரேச்சர் மாறல, அதே டெம்பரேச்சர் தான் இருக்கு. கேப் குறையிறதுனால பார்ட்டிகலால ஹையர் ஸ்டேட்ஸ் கூட ஆக்சஸ் பண்ண முடியும். Okay, therefore partition function will increase. Right?
Yes sir, thank you.
Yeah. Yes, any other doubts?
சார் இந்த இங்கிலீஷ் கொஸ்டினுக்கும் டிஸ்டிங்விஷபிளுக்கும் ஏன் சார் நம்ம வந்து q = q power n போறோம், இன்னொரு q = q power n by n ஃபேக்டோரியல் போறோம்? அது n ஃபேக்டோரியல்
ஆக்சுவலா இந்த n ஃபேக்டோரியல் ஏன் டிவைட் பண்றோம்னா, இப்போ நான் சும்மா ஒரு அண்டர்ஸ்டாண்டிங்காக சொல்றேன். இப்போ இது டிஸ்டிங்விஷபிள் பார்ட்டிகல் AB டிஸ்டிங்விஷபிள் வச்சுக்கோங்களேன். இது ஒரு அரேஞ்ச்மெண்ட், கரெக்டா? வாட் அபவுட் திஸ்?
இது அனதர் மை क्वेश्चन. இது
வேற ஒரு அரேஞ்ச்மெண்ட்ல டிஸ்டிங்விஷபிளா இருந்தா, சப்போஸ் ரெண்டு பார்ட்டிகல் இன்டிஸ்டிங்விஷபிள் வச்சுக்கோங்க, ரெண்டு பார்ட்டிகல் இன்டிஸ்டிங்விஷபிள், நான் இப்போ AB எல்லாம் போடல, வெறும் ரெண்டு டாட் மாதிரி வச்சிருக்கேன். ரெண்டு இன்டிஸ்டிங்விஷபிள்னா இதை நீங்க ஸ்வாப் பண்ணாலும் இப்படி மாத்தினாலும் அதே தான் வரும்ல. அப்போ இதுக்கு வந்து பாருங்க, நம்பர் ஆஃப் மைக்ரோஸ்டேட் 1 தான், இங்க எத்தனை இருக்கு?
2. அப்போ
என்ன ஆகுது பாருங்க, டிஸ்டிங்விஷபிள் பார்ட்டிகலா இருந்தா நம்பர் ஆஃப் மைக்ரோஸ்டேட் நிறைய இருக்கும், இன்டிஸ்டிங்விஷபிளா இருந்தா நம்பர் ஆஃப் மைக்ரோஸ்டேட் குறைஞ்சிரும், கரெக்டா? இப்போ அந்த ஃபார்முலா போய் ரீகனெக்ட் பண்ணுங்க, ரீகனெக்ட் பண்ணி பாருங்க. q = q power n, இது டிஸ்டிங்விஷபிள். இன்டிஸ்டிங்விஷபிளுக்கு குறையணும்ல வேல்யூ, n ஃபேக்டோரியலால் டிவைட் பண்றீங்க, டிவைட் பண்ணிடும் குறைஞ்சிடும் வேல்யூ. அதுதான் ஜஸ்ட் அண்டர்ஸ்டாண்டிங்காக நான் அப்படி சொல்றேன். பட் we have derivation for this. நமக்கு ப்ராப்பர் டெரிவேஷன் இருக்கு, பட் டெரிவேஷன் பண்ணாம உங்களுக்கு ஈஸியா அண்டர்ஸ்டாண்ட் பண்ணிக்கலாம் சொல்லியிருக்கேன். எஸ்பா. Any other doubts?